All right, so this is going to be a quick summary of Kirchoff's loop and junction rules. The loop rule states that the sum of the voltages around any closed loop must add up to 0. This is an extension of the law of conservation of energy. Okay. And basically what it says is that in mathematical form, the sum of the voltages must equal 0. What you're getting here is that, so the voltage, the 6 volts here, is going to give an electromotive force from the 6 volts. It's going to pick up the 3 volts here, giving us 9 volts, and it's going to continue around the circle counterclockwise. Okay, so the battery provides energy, okay, and what do the resistors do? The resistors change the energy to something else. Like if it was a light bulb, it would change it to light. So that's where that conservation of energy kind of comes in. So if we have these 9 volts over here on the left-hand side, these guys have to change 9 volts on the right-hand side. And here's the logic why. If they don't change it, if you don't end up with 0 volts on the other side, if you don't end up with 0 volts coming back into the battery, what are you doing to the battery? You're shoving more energy into a battery that can only push 9 volts. So you're just going to keep shoving that energy in, shoving the energy in, and finally the battery blows, catches on fire, or does something else that's kind of nasty. So that's where the conservation of energy comes in. So let's go ahead and we're going to use the loop rule to calculate the current going around this circuit. Okay, so basically batteries that are going in the same direction, they add voltage. Resistors change voltage or change energy into something else and remove the energy from the system. So what we have here is we've got V1. Okay, I'm going to call this V1, V2, R1, R2. So we have our 2 voltages are both pointed correctly, oriented correctly, negative, positive, negative, positive. So those guys are going to add up. Now here comes our 15 ohms. Now we don't know what the voltage is, but we do know Ohm's law is V equals IR. So I don't have to use V, I can just put in IR. And this, again, the resistor changes the energy or removes it from, or changes the energy, or kind of basically removes the energy. So here's I times R1, and the same thing is going to happen at the next one. Whoops, I times R2 minus I times R1, and that will equal 0. Let's put our numbers in here. So V1 is 6, V2 is 3. Our current's what we're looking for. Our R2 resistance is 15 ohms. Minus our current times our 10 ohms is equal to 0. So we got 9 minus 25 times the current is equal to 0. And now we just solve. 9 is equal to 25 times current. Therefore, current is equal to 0.36 amps. Okay. And that's how you use the loop rule. The basic idea to remember is that batteries generally add energy to the system, and resistors change energy. They take energy and turn it into something else. The end goal being that once you're done with all the resistors, you have 0 volts. Okay. All right. So that is our loop rule. Let's take a look at the junction rule. The junction rule states that the total current coming into any junction must equal the total current coming out of any junction, or current in equals current out. Is the other way of saying this. Current in equals the current out. This one is a continuation of the conservation of charge. The law of conservation of charge. And since charge is based off of atoms, and atoms go to mass, we can also say it's the law of conservation of charge, or mass, depending on how you're arguing it. Does that make sense? That's kind of both of them. Okay. Okay, so here's what goes. So first off, let's talk about what a junction is. A junction is any place, anywhere a path splits or joins. Now, for example, before we get too far into this one, we're going to go up just a little bit. So if you're looking at the series circuit that we had at the beginning, if you notice, there's no actual splits anywhere. This is one continuous path all the way here. There's no splits. But if we look at that parallel circuit that's below, we can see that we have, here's one path, and then here's another path. So that's what we're talking about, the junctions, okay? So that's our junctions in and out. So that means this part right here, they're identified actually. Here's a junction, and here's a junction, which is why when you're looking at this, we know that I1, current in is I1, and our current out has to equal that, I2 plus I3. Okay, so the goal of this one is to figure out what exactly is our total current. Okay, so I don't know I1, but I can use Ohm's law to figure out I2 and I3. Ohm's law and the loop rule. Okay, now the loop rule, let's take a closer look at that really quick. The loop rule says that the voltages around any closed loop must add up to 0. Well, how many closed loops do we have? Okay, so what that's kind of saying here is that the voltage going across this path here is going to be 12 volts. And the voltage going across this path here is going to be 12 volts. So you can take my word for it and just say that, hey, it's a closed loop, therefore voltage has to be the same. Or we could talk about what conceptually. Remember, it's energy. The voltage is a potential difference, okay? So along this path here, there is nothing to change the energy. All this part that I just highlighted, it's just wire, which is a conductor. There's nothing in there to change the energy, so the energy doesn't change. So we get the same 12 volts, all right, of electric potential being pushed over. That's why that works. So we're going to use the idea that 12 volts is going to be the same across both of those.